All right, so today we are going to crack open a puzzle that sits right at the very heart of modern physics. And here's the kicker. It's over a century old, and some folks argue it was never really solved at all.
I mean, just think about it. What if the theory that basically defines our entire universe, the one that gave us E equals mc squared, black holes, all of it, what if it's all built on a simple, flawed assumption from 100 years ago? It's kind of wild, right? So, let's put on our detective hats and follow the clues.
Okay, so to get our bearings, let's start with the official story. Back in the early 20th century, the behavior of light was just a massive headache for physicists. It wasn't playing by the rules. And then, one man came along with an answer that would change everything.
And that answer, of course, was special relativity. Now, at its core, it's got two really powerful ideas. First, the laws of physics are the same for everyone as long as you're not accelerating. Makes sense. But the second one, well, this is the big one. The speed of light in a vacuum is always the same. For everybody. It doesn't matter if you're standing still or zipping past in a spaceship, you'll measure the speed of light at the exact same number. It's a fundamental constant of the universe.
But here's where our story takes a turn. What if there was another path, a totally different way of thinking about all this that kind of got, well, pushed aside in the excitement to embrace Einstein's new universe? Let's go ahead and take a look at this forgotten what if.
So what you're looking at here are two completely different ways of seeing the universe. On one side, you've got Einstein. In his world, reality itself, space and time, literally warps and bends to make sure the speed of light stays constant for every single person. It's wild. But on the other side, you have this absolute field model. Here, the universe is like a fixed stage. Light moves at a constant speed relative to the stage, not to you. So if you're moving, your measurement of light speed will change. It's a much more, well, intuitive, classical idea. And this idea really gets to the heart of it. The field is the stage. Matter is just an actor moving across it. I love that analogy. It's like the universe is this huge, unchanging stage, and everything in it, you, me, planets, trains, we're all just actors moving around on it. The rules of the stage itself are absolute, but what an actor experiences totally depends on how they're moving.
So, okay, we have these two profoundly different views of reality. How do they actually stack up against each other?
Well, let's run a little thought experiment and see them in action. But first, we need a quick concept to wrap our heads around. See, an object doesn't just exist at one single point in time, right? It exists continuously. Physicists have this cool way of visualizing this called a world tube. It's like a path that an object traces through space-time. This is going to be really important because it helps us figure out where something actually is versus where we just see it at any given moment.
All right, let's set up our experiment. It's pretty simple, really. Picture a long, straight train track out in space. On that track, we've got a train, and it's moving fast. Now, at the exact instant the center of the train lines up perfectly with the center of the track, bam! A flash of light goes off from that single shared point.
Okay, so the light flashes. We let it travel for, say, 1,000 seconds. Now, here is the million-dollar question. If you're an observer sitting right in the middle of that moving train, where are those two pulses of light now? The one that shot forward and the one that shot backward.
Okay, so according to Einstein, the observer on the train gets a really wild answer. For them to measure the speed of light as constant, reality itself has to twist and bend. They have to conclude that their clock started ticking slower and the rulers literally shrank compared to the track outside. It's only through this crazy distortion of space and time that the math works out and the light appears to be exactly where it should be, 1,000 light seconds away in both directions.
But now let's ask the observer in the absolute field model. Their answer is, well, a lot more straightforward. They'd say, look, I'm moving through the field. The light pulse going forward is racing away, but I'm chasing after it, so the distance between us is obviously going to be smaller. And the pulse going backward? Well, I'm moving away from that one, so the distance between us is going to be larger. It's simple, it's intuitive, and you don't have to rewrite the fundamental laws of time and space to make it work.
See, once you entertain this alternative view, it forces you to go back and re-examine the very evidence that led us to Einstein in the first place. So let's do that. Let's take a look at a really famous experiment, but through this new lens.
We're talking about the Michelson-Morley experiment from way back in 1887. This thing is legendary in physics. It was designed to detect something called the ether wind, basically the effect of the Earth moving through this absolute field. But it failed. It found nothing. And that null result is what paved the way for Einstein. But what if they didn't find anything because the experiment itself had a simple, fundamental flaw?
This potential flaw all comes down to something called information delay or stellar aberration, and it's actually pretty easy to understand. Imagine you're aiming a light beam at a moving mirror. You aim at where you see the mirror, right? But that image you're seeing is from the past. It took time for the light from the mirror to reach your eyes, so by the time your light beam actually arrives at that spot, the real mirror has moved on. You're essentially aiming at a ghost.
And this is the absolute crucial point. The entire experiment was built on the assumption that the light beam would hit the dead center of the moving mirror and make a perfect round trip. But if the whole lab is hurtling through an absolute field, it couldn't have hit the center. Because of that delay, the beam would have hit off-center or maybe even missed the mirror entirely.
So if you follow that logic, it leads to a conclusion that seems kind of unavoidable. If there is an absolute field, then the two light beams in the experiment had to travel different distances. And since their speed through the field is the same, there's just no way they could arrive back at the detector at the exact same time. It's physically impossible, which means that famous null result might not prove there's no field at all. It might just prove that the experiment was designed in a way that it was guaranteed to fail.
And this pushes us into some really deep, almost philosophical water. It makes you ask, what is the goal of physics anyway? I mean, what kind of reality are we actually trying to describe with all our equations?
So to really get a handle on this debate, the source material we're looking at proposes this really interesting framework. It says physics is actually trying to describe three different worlds. You've got the symbolic world. That's the pure, abstract world of math and coordinates. Then there's the imaginary world. That's the world we actually perceive, how things look to us. And finally, there's the real world, the world of actual physical events, which has to account for messy stuff like information delay.
Now here's where it gets really cool. When you place our two competing theories into this framework, a really fascinating distinction just pops out. Einstein's relativity, it's like a perfect, beautiful map of that symbolic, mathematical world. But the absolute field model, it's trying to do something different. It's an attempt to describe the real world with all its physical, messy detail.
Let me put it another way, because this is the key takeaway. Einstein's theory is brilliant at describing the image we see, the final information that hits our eyeballs or our detectors. The Einstein model, on the other hand, is trying to describe the actual existence that creates that image. It's the difference between describing the picture on the TV screen and trying to describe the electronics inside the TV that make the picture happen.
And so that leaves us with a massive, and I think really profound question. What should physics even be doing? Is its job just to describe the world as it appears to us, to perfectly predict the information we receive? Or should it be trying to describe the world as it truly is, the objective reality that's out there whether we're looking at it or not? A full century after Einstein, that question, unbelievably, feels more open than ever.